Hey guys, welcome back to chapter 10. We're going to continue our journey through the intermolecular forces. We've talked about London dispersion, weakest, everybody does it. We've talked about dipole, so a little bit more exclusive. You have to be a polar molecule. And then we talked about how to identify polar molecules, so hopefully you did the review of that. Now we're going to talk about our next intermolecular force, and that is called hydrogen bonding. Disclaimer, it is not actually a bond. It is still this intermolecular interaction. So it's an attraction, attractive force, still positives attracted to negative. We just call it hydrogen bond because that's what we do. All right, so hydrogen bonds. Hydrogen bonds really are just an extreme dipole-dipole interaction, right? So we got a little bit more exclusive with the dipole. You had to be a polar molecule. Now we're going to get even more exclusive. So this is like an elite group of atoms that can participate in hydrogen bonding. But really, at the end of the day, it's just a very extreme dipole-dipole interaction. The reason for this kind of elitist category is we're going to have atoms that are very, very small, and they have they're highly electronegative. So that's going to create very large differences in the electronegativities. So that separation of charge, that dipole moment, it's going to be kind of an extreme case. So that's why these elitists are in this category. So without further ado, I will introduce you to the elitist category. So the atoms that participate in the hydrogen bonding are fluorine. Ooh, that's a little far away here. Hang on. Fluorine. Oxygen and nitrogen. So fluorine, oxygen, and nitrogen are our elite category. These atoms will be bound to a hydrogen atom. So fluorine connected to a hydrogen, oxygen connected to a hydrogen, or nitrogen connected to a hydrogen. Those are the only three atoms that can participate in hydrogen bonding. So if you guys look at your electronegativity chart, what you'll see is fluorine has the highest electronegativity out of all of the atoms. So very, very high electronegativity, and that's going to cause the biggest electronegativity differences. Very close to fluorine is oxygen and nitrogen, so those also are very electronegative, causing that large difference. Okay. The other thing about these atoms that kind of plays into this hydrogen bonding is the fact that they're really small atoms. So when we see this kind of interaction between a nitrogen and a hydrogen from another molecule, this nitrogen is very small. So its valence electrons are in that first or second energy level. And with the valence electrons being in that second energy level, this little tiny hydrogen can get very, very close to this little tiny nitrogen. So that also adds to this effect. So the electronegativity differences are very large. These atoms are teeny tiny, so we can get really close together. Okay. And then the last piece here in this hydrogen bond that makes them stronger, or an extreme version of dipole-dipole, is the fact that hydrogens can get what we call de-shielded. Okay, so if you guys remember, hydrogens, that's the first element on the periodic table. It has one proton, one electron. When it is in a bond with these other atoms, grab my pen here. When it's in a bond with these other atoms, so let's just put them with oxygen, for example. Oxygen is our big brother, right? He's more electronegative. So oxygen is going to have that partial negative. Hydrogen is going to have that partial positive. So remember, the electrons are being kind of pulled this way or hogged that way. So hydrogen has one electron. So that one electron that hydrogen has is being pulled towards the oxygen. He doesn't have any other electrons to kind of balance that out. So all that's left with this hydrogen atom, if the electrons are being pulled towards the oxygen, all that's left in this hydrogen atom is a proton, right? And so that right there is what we call de-shielding. His electron is being pulled towards the oxygen, and then that one proton in the nucleus is de-shielded or exposed, right? So he kind of becomes like an extra positive atom, right? So we got this like center of positive charge that's exposed. So that adds to this as well. So between the fact that there's a large electronegativity difference between nitrogen and hydrogen, fluorine and hydrogen, oxygen and hydrogen. So large electronegativity difference. These are teeny tiny atoms. They can get really close together. And then the fact that when hydrogen kind of loses that electron, his positive center is exposed. He's de-shielded. Those three factors kind of work together to create this like extreme dipole moment. And it's so extreme and so important that we call it hydrogen bonding. We call it its own thing. Okay. So here's that like can approach then bond closely. That has to do with the small. So big difference, small atoms, and then that hydrogen can get de-shielded. So here's just kind of a summary of all the things that I said. You can pause the video and spend some time on this slide kind of reading through it. But again, this is just a repeat of what I said. Hydrogen bonding. We've got this elitist category. We've got fluorine, oxygen, nitrogen that can participate in hydrogen bonding. And we've got some really cool things that hydrogen bonding can do. So when you guys get to organic chemistry and into your biochemistries, hydrogen bonding becomes a really important factor in why things do what they do. So let me just kind of give you a preview of what hydrogen bonding is capable of, why it's so important and has its own little elitist category. So biology, right? We talk about DNA, okay? So DNA has two kind of backbones, right? Those two backbones kind of coil around in this double helix. And with those two bones coiled around in this double helix, we get DNA, right? So one of the important properties of DNA is the fact that we can unzip those two backbones, those two phosphate backbones. We can kind of unzip them, pull them apart. They can do their little replicating or whatever they need to do on the side, and then we can zip them back up and protect them for future use. Ever wondered how and why we can unzip and rezip these two backbones? Well, it has to do with hydrogen bonding. So you know that there's these complementary base pairs, right? Guanine and cytosine will connect with one another. G and C create a pair. And adenine and thymine come together. A and T create a pair. And those are the only options for pairings. Like guanine is not going to pair with thymine, or adenine is not going to pair with cytosine. Like there's these very specific pairs that get made as these two phosphate backbones come together. Well, the reason that those base pairs are complementary to one another is it maximizes the number of hydrogen bonds. So what holds these two phosphate backbones together is a series of hydrogen bonds. So with the guanine and cytosine, what we see here is oxygen, hydrogen, hydrogen, nitrogen, oxygen, hydrogen. So those have the opportunity for 3 hydrogen bonds to form, and they're lined up perfectly for those 3 hydrogen bonds to form between the 2 base pairs. We come down here to adenine and thymine, and we see the same concept here, but we've got 2 areas where hydrogen bonding can happen. So what holds the 2 backbones of DNA together is hydrogen bonding. Hydrogen bonding is strong enough to connect these strands to hold DNA, which is a very, very important biological molecule. It's strong enough to hold this DNA together. But that's not it. It's also weak enough to allow those 2 strands to unzip. If these were covalent bonds holding the 2 strands together, we wouldn't have enough energy to break those covalent bonds to unzip it. That would just cost too much energy. Replication wouldn't happen. But because hydrogen bonds are intermolecular forces, right? It's just an attraction. It doesn't take quite as much energy to pull that those hydrogen bonds apart. And then we can kind of snap them back into place. So hydrogen bonding plays such a vital role in this DNA and allowing the 2 backbones to come together and be rigid, but also allowing for them to be unzipped so replication can happen. So hydrogen bonding, super, super important. It's our little elitist category. It's the strongest of the intermolecular forces we've talked about so far. I hope you guys found this helpful.